Welcome to Naradar Academy. In this video, we are going to discuss about complex integration, in that evaluation of definite integrals. See, here what we are going to do is some complicated integration of real valued functions can be simply completed by converting it into complex integrals. So that is the procedure we are going to see here. There are three different types. The first type is integral 0 to 2 pi f of cos theta sin theta d theta. That is, the integrand is a function of sin theta and cos theta. In that case, the substitution we are going to make here is z equal to e power I theta over the unit circle mod z equal to 1. Mod z equal to 1 means what? Unit circle with center at origin and radius equal to 1 unit. Okay, so this is the substitution we are going to make. So this cos theta will become z plus 1 by z by 2 and sin theta will become z minus 1 by z by 2i. So by rewriting all the sines and cos in terms of z, we will get completely a function of z. Here it is limit 0 to 2 pi, no, but here when you convert it into complex integral, it will become over the curve C, where C is the unit circle mod z equal to 1. Then we can evaluate this integral by using the residues. Okay, right. Then the second type is integral minus infinity to infinity f of x dx, where f of x is the quotient of g of x by h of x. The condition is here g of x and h of x are polynomials in x and the degree of the denominator is at least 2 greater than g of x. That is, if this degree, numerator degree is 3, then the denominator should be at least 5. Okay, 2 more than the numerator. In that case, again, the function can be, the integral can be evaluated by using complex valued functions. Simply in this case, what we are going to do is change all the x to z. Okay, no other thing is required. Whatever you have, a function in f, function in x, change everything in terms of z. Okay, then the integral will become integral over c f of z dz is equal to integral minus r to r f of x dx plus integral over c1 f of z dz. Then as r tends to infinity, value of this portion will become 0. Okay, we will have only these two things, and this can be evaluated by using residues. Okay, this is the case when the poles of f of z doesn't lie on the real axis. Okay, that is, the poles are not lying on the, this is the case when the poles lying on the real axis. That is the second case. When there is no pole on the real axis, this is the procedure. Okay, suppose when you have poles on the real axis, we have a separate formula. For the pole on the real axis, you take a circle C2, okay, around this pole on the real axis. In that case, the integral can be written as integral over c f of z dz equal to integral minus r to r f of x dx plus integral over c1 f of z dz plus integrals over c2 f of z dz, where this is 2 pi a into sum of the residues. Okay, and this is the pole on the real axis. No, for this one the formula is minus pi a into residue, sum of the residues on the real axis. Okay, right. Then the third type, the type 3 is integral minus infinity to infinity g of x by h of x, again quotient of two polynomials along with either sine or cosine function. In that case, what we are going to do is, we are going to solve this problem exactly in the type 2 method, but for the sin x or cos x, we are going to replace it as e power I a z. Okay, and then we will do. You can understand this concept better when you do the problem. So let us do the problems one by one. This is the problem under model 1. Evaluate integral 0 to 2 pi d theta by 5 plus 4 sin theta. So look at this one. This is a real valued function only. No, we have to evaluate between 0 to 2 pi. Okay, so it comes under type 1. So in that one, what is the substitution? We have to take z equal to e power I theta. So what is sin z? Z minus 1 by z by 2i. So let us do the simplification here. So it will be z square minus 1 by 2i z. Okay, this is sin theta, but here what we have, 5 plus 4 sin theta. So 5 plus 4 sin theta will become 5 plus 4 into z square minus 1 by 2 I z, right? Then by taking LCM, what we get? Here this 2 and this 4 get cancelled, no? So what we get? 5iz plus 2z square minus 2 by iz. So this is the value of this function. Now what about d theta? See, z equal to e power I theta, no? So dz will become, differentiate this, I e power I theta into d theta. So d theta is equal to dz by iz. So all the values within the integral sign we have evaluated here. Let us substitute it here. Now instead of this 0 to 2 pi, what we have to substitute? Over the curve C, where C is the unit circle, mod z equal to 1. For all the problems, this is the same. That is, over the unit circle only we are evaluating, because that is how we have taken z equal to e power I theta. Right? Okay. So let us substitute the values one by one. Instead of d theta, I have to substitute dz by iz divided by 5 plus 4 sin theta is 5iz plus 2z square minus 2 by iz. So this iz get cancelled. So we have integral over C 2z square plus 5iz minus 2. Now let me take this function as f of z. Now this is exactly like a complex integration, no? So over the circle, unit circle, mod z equal to 1, we have to evaluate. For that, what we have to do? By equating the denominator, we have to find out the poles. Okay, equate the denominator to 0. So 2z square plus 5z minus 2 equal to 0. Now we have to factorize this. See, 2 2s are 4, minus 4, no? So minus 4. But here you see you are having 5 I, no? So instead of taking it as simply minus 4, I am going to take it as 4 I square, because I square is minus 1, no? So minus 4 can be taken as 4 I square, which can be split up into 4 I plus 1 I. So that this 5 plus 5 iz we can get. So 2z square plus 4iz plus iz minus 2 equal to 0. So after simplification, 2z into z plus 2i plus I into z plus 2i. Again here also it is iz minus 2 only, no? This minus 2 can be written as what? 2i square plus 2i square. So out of that, if you take I outside, it will become z plus 2i equal to 0. So z plus 2i into 2z plus I equal to 0. So what are the poles we are getting? Z equal to minus 2i and z equal to minus I by 2. Okay, we have two poles for the given function f of z. Out of these two, we have to check which of them are lying inside mod z equal to 1 and which of them are lying outside mod z equal to 1. See, mod z equal to 1 means what? Circle with center at origin and radius equal to 1 unit. See, this is 2i, no? Minus 2i, no? That means what? 0 comma minus 2. 0 comma minus 2 is lying outside the circle. And this is minus I by 2 means what? 0 minus I by 2, that is 0 comma minus 1 by 2. So minus 1 by 2 means this is lying inside. I have already posted one video for evaluating complex integrals. There I have clearly explained how to identify whether the poles are lying inside the given circle or not. Okay, you watch the video. I have given the link in the description box. Okay, so first, after finding the poles, we have to check which of them are lying inside and outside the circle. Now only one pole is lying inside. Only for the poles which are lying inside C, for them only we are going to find the residue. For the other poles, no need to find the residue. So I am going to find the residue at z equal to minus I by 2. This is a simple pole only, no? So the residue is given by limit z tends to minus I by 2, z plus I by 2 into f of z. Now what is my f of z? F of z is 2z square plus 5iz minus 2. So for evaluating the residue, you write the value of f of z in its factors form. Okay, so it is z plus 2i into 2z plus I. Okay, now you substitute these two terms get cancelled, no? After cancelling, it will become limit z tends to minus I by 2, 1 by z plus 2i. Now substitute z equal to minus I by 2. So minus I by 2 plus 2i, it's equal to 1 by 2 into 3i by 2. So finally what I am getting? 1 by 3i. So this is the residue. Next, so what is integral over C f of z dz? 2 pi a into sum of the residues. So 2 pi a into 1 by 3i. So I get cancelled. Finally what we get? Integral 0 to 2 pi f of z dz is what? D theta by 5 plus 4 sin theta is equal to 2 pi by 3. Okay, that's all. Then the next problem. Evaluate integral minus pi to pi d theta by 1 plus sin square theta. Okay, so this problem also can be solved by using complex integration. But before using complex integration, we have to do some rearrangements, because here the limit is from minus pi to pi, no, but we can evaluate only from 0 to 2 pi. If the limit is different, we have to change everything. We have to bring it to the form that I have prescribed in the first page. After that only you can solve the problem. Okay, so before that, let me rewrite this sine square theta. The sine square theta can be written as 1 minus cos 2 theta by 2. Okay, then you take LCM and rewrite. So it will be 2 plus 1, 3 minus cos 2 theta by 2. So I am getting it as integral minus pi to pi 2 d theta by 3 minus cos 2 theta. See, here in the place of theta I am getting 2 theta, no, and the limit is from minus pi to pi. And this is also not in the proper form. I have to get it like 0 to 2 pi, no. So what I am going to do is, let me assume phi equal to 2 theta. Okay, then what happens here? 2 d theta equal to d phi. Instead of this 2 d theta, I can write it as d phi. And here the limits, we have to change the limits also, no. Theta varies from minus pi to plus pi. So what about 2 theta? 2 theta varies from minus 2 pi to plus 2 pi. That means phi varies from minus 2 pi to plus 2 pi. Okay, so I can substitute it here. Instead of 2 d theta, put d phi 3 minus cos phi. Okay, now you see this integrand is a even function only, no, because cos phi, cos is an, cosine is an even function. So when you have even function, instead of writing as minus 2 pi to plus 2 pi, I can write it simply as 2 times integral 0 to pi. Okay, if the integrand is even, integral minus 2 pi to plus 2 pi can be written as 2 times integral 0 to 2 pi d phi by 3 minus cos phi. Okay, now I get the integral in the required form. That is, the limit is from 0 to 2 pi, and this is simply function of cos theta, cos phi. Okay, now let us make the substitution. What is the usual substitution we have to take? Z equal to e power, here it is phi, not theta. So Z equal to e power I phi. So what is dz? I e power I phi d phi. That means dz equal to Iz d phi, or d phi equal to dz by Iz. And again for cos phi, I can write z plus 1 by z by 2 or z square plus 1 by 2z. So let us substitute all these values here. Here the limit is from 0 to 2 pi, no. Instead of that, here we have to take over the circle C, where C is the unit circle, mod z equal to 1. So here this will become 2 times integral over C dz by, okay, dz by, take LCM here, 6z minus z square minus 1 by 2z into Iz. So this is equal to, this 2 become 4, 4 by I into, this z get cancelled, dz by minus z square minus 6z minus 1. So I can keep this minus 4 by I outside. So it will be simply 1 by z square minus 6z minus 1 into dz. So let me take this integral, this value of the function as f of z. So now I have to evaluate this by using complex integration. For that, first I have to identify the poles which are lying inside C. For identifying the poles, equate the denominator to 0. So z square minus 6z minus 1 equal to 0. That implies z equal to 6 plus or minus root of 36 minus 4 by 2 equal to 6 plus or minus 4 root 2 by 2, that is 3 plus or minus root 2. So these two are the simple poles that we are getting for this function f of z. Now out of these two poles, we have to identify which one is lying inside and which one is lying outside. See, by mere calculation we can see root 2 value is 1.414, no. So this value 2 into 1. It will be more than 2. So 3 plus 2 will become what? It will become more than 5. More than 5 means it will lie outside the unit circle. Unit circle means what? Radius equal to 1 unit. And this 3 minus 2 root 2 will be definitely less than 1, because this value is 1.414, no. When you multiply it with 2, it will be more than 2 only. So when you subtract 3 minus 2, it will become less than 1. Positive number but less than 1. That means this is lying inside the circle. So for the pole which is lying inside C, we have to calculate the residue. So residue of f of z at z equal to 3 minus 2 root 2 is equal to limit z tends to 3 minus 2 root 2 into z minus 3 minus 2 root 2 into 1 by, write f of z in the factors form. Okay, then these two terms get cancelled. We simply get z minus 3 plus 2 root 2. Now substitute z equal to 3 minus 2 root 2. So 3 get cancelled. So finally what we get? Minus 1 by 4 root 2. So we find out the residue. The formula is integral over C f of z dz equal to 2 pi a into sum of the residues. So 2 pi I into, here only one residue is there, so minus 1 by 4 root 2. So what we get, minus pi I by 2 root 2. Okay, but what is our integral I? I is equal to minus 4 by I into integral over C f of z dz. So minus 4 by I into minus pi I by 2 root 2. So finally what we get? Root 2 into pi. Okay, that's all. Then the next problem, this is of type 2 problem. Evaluate integral 0 to infinity dx by x square plus 1. First you have to check whether the conditions of the type 2 are satisfied or not. What is the condition? Numerator and denominator should be polynomials of x. Here the numerator is 1 and the denominator is x square plus 1. Second condition is degree of the denominator should be at least 2 greater than the numerator. Now in the numerator only number 1 is there, no, it is of degree 0. Here x square plus 1 degree 2. So the denominator exceeds the numerator by degree 2. Okay, so all the requirements are satisfied. But the limit is from 0 to infinity. But for type 2, we need from minus infinity to infinity. No problem. This is an even function only, no. So by using the property integral 0 to infinity dx by x square plus 1 can be written as half of integral minus infinity to infinity dx by x square plus 1. Okay, so after verifying whether it satisfies all the requirements for type 2, what you have to do? Simply write whatever is there in terms of x, write in terms of z. So let me take f of z equal to, what is this function? 1 by z square plus 1. Equate the denominator to 0. Z square plus 1 equal to 0. So z square equal to minus 1. That means z equal to plus or minus I are the simple poles. Here we have to identify which of them are lying inside C. For second type, C is my upper half plane. Okay, C is upper half plane. Otherwise, I will say, see, I have drawn one semicircle, no? Let me take that semicircle as C1. Okay, C1, no, not the semicircle, the entire circle. The full circle is C1. It's a circle with radius R. Okay, now I am going to take only the semicircle. Okay, that means what? Upper half plane. Okay, this is bounded by the line segment minus r2 plus r and this arc. Okay, arc of the semicircle, right? So in this portion only you have to verify which of the poles are lying inside or not. For type 2 and 3, it's very easy to verify whether it is lying inside or outside. That means it is lying on the upper half plane. It can be anything. Whether it lies on the upper half plane, it is inside. Lower half plane means what? Outside. Okay. So obviously this plus I is lying in the upper half plane and minus I is lying in the lower half plane. So only the plus I you have to take and you have to find the residue only at that point. So residue of f of z at z equal to I equal to limit z tends to I, z minus I, 1 by z plus I into z minus I. So finally 1 by z plus I, now substitute the limit, it will be 1 by 2I. So integral over C f of z dz equal to 2 pi I into sum of the residues. So 2 pi I into 1 by 2I equal to what? Pi. Now what is this limit integral over C f of z dz? This is nothing but the integral over this semicircle. How will you write this semicircle? It is nothing but minus r to r. This is one of the boundaries, no? So minus r to r f of z dz plus over this circle. Okay, over this circle, what is this? C1. C1 I have taken, right? Cauchy's lemma states that the value of this integral tends to 0 as the radius r tends to infinity. Okay, instead of this I can put 0. Okay, what about this one? As r tends to infinity, this minus r to plus r will become minus infinity to plus infinity. What about this f of z dz? See, this is the minus r to plus r means what? This is the line segment from minus r to plus r, no? It is completely lying on the real line. In real line, the value of the imaginary part is 0. That means z is simply x. So instead of writing f of z dz, what can you write? F of x dx. Okay, so this point is important. F of x dx. Now integral over C f of z dz, this we have already evaluated as pi. So pi is equal to integral minus infinity to infinity f of x dx. Okay, right. So f of x dx, integral minus infinity to infinity f of x dx equal to pi, or simply I is equal to 1 by 2. I is nothing but integral 0 to infinity only, no? 1 by 2 of this value, it's equal to what? Pi by 2. Okay. Then next problem, evaluate integral 0 to infinity x square by x power 6 plus 1 dx. First check the limits. we need it from minus infinity to plus infinity, but it is 0 to infinity. It's okay, we can change because the integrand is an even function, no? So instead of this 0 to infinity, I can write half of integral minus infinity to infinity. Okay, that is good. Next one, numerator and denominator must be polynomials. Yes, that is also true. Next one, degree of the denominator should be at least 2 greater than the numerator. Here degree is 2 in the numerator, degree is 6 in the denominator. So it is also true. So all the conditions are satisfied. Now I can proceed by type 2 method. For type 2, replace all x by z. So f of z equal to z square by z power 6 plus 1. Now find all the poles. For finding the poles, equate the denominator to 0. So z power 6 is equal to minus 1. See, whenever you have in terms of complex numbers, see minus 1 is there, no? Minus 1 means when will you get? For what value you will get? That is cos pi. Cos pi equal to minus 1. But instead of writing it as cos pi, how will you write? Cos pi plus I sin pi, that is e power I pi. Not only for pi, 3 pi, 5 pi, 7 pi, for all those things you will be getting, no? So this is nothing but instead of minus 1, e power 2n plus 1 I pi. Can you understand? Minus 1 is nothing but cos pi plus I sin pi. Not only for simply pi, 3 pi, 5 pi, 7 pi, etc. It is true. So z power 6 is equal to, instead of minus 1, how will you write? E power 2n plus 1 into pi I. This n varies from 0, 1 to etc. up to 5 only, because this is 6th degree polynomial, no? So it will be having only 6 roots. So z power 6 is equal to e power 2n plus 1 into pi I. So z is equal to e power 2n plus 1 into pi I by 6. Right? Okay. So now substitute the values for n. N equal to 0, 1 to etc. up to 5. So what will you get? The poles are e power pi I by 6, 3 pi I by 6, 5 pi I by 6, 7 pi I by 6, 9 pi I by 6, and finally 11 pi I by 6. These are the poles. No need to find out the values. Okay. Let me tell you how to check whether how many of them are lying inside C and outside C. Okay. This line is not required. That is why I have written here. This is not required. Directly we can write which are lying inside and which are lying outside. See, look at the first rule. Pi by 6, no? Pi by 6 means what? 30 degree. 30 degree means it will lie in the first quadrant only. You know, no, in the first quadrant and second quadrant only we have to take the poles. That means what I said, only the poles on the upper half plane are taken to be inside, lower half plane are outside. Upper half plane means what? Only in the first and second quadrants. If the pole lie in the first and second quadrant, it will be taken inside. So this is pi by 6 means what? 30 degree. 30 degree means what? First quadrant, inside. So it is inside. You omit this line. This is not required. Next one. Pi by 6 into 3. Pi by 6 means what? 30. 30 into 3 what? 90. 90 means what? It is also on the upper half plane. So 3 pi by 6 is also on the upper half plane. Next one is 5 pi by 6. So 5 into 30 is what? 1. 5 30s are what? 150. 150 means it is in the second quadrant. That means upper half plane. So it is also in the what? Inside the curve C. Next one is 7 pi by 6. 7 means what? 7 into 30. 210. 210 will lie in the third quadrant. Third quadrant means lower half plane. So outside. Next one is 9 into 30 is 270. 270 is also lying on the fourth quadrant. And 11 pi by 6. 11 into 30. 11 330. Fourth quadrant. So only the first 3 roots are lying inside C. The other 3 are lying outside C. What do you mean by inside? Upper half plane. Outside means what? Lower half plane. It is enough if you identify with this. No need to write the values and check. Okay. I hope you understand this point. So these are the simple poles which are lying inside C. At these points I have to find out the residues. See, my function is z power 2 by z power 6 plus 1. So for finding the residue, let us take the numerator as h of z and denominator as k of z. In this type of problem, the residue is given by the formula h of a by k dash of a. Now here h of z is the numerator z square and k of z is the denominator z power 6 plus 1. So what is k dash of z? 6 z power 5. Okay, now let's find the residue at all the 3 poles inside C. So f of z at e power pi I by 6 is equal to e power, this is z square, no? So it is 2 pi I by 6 by, this is 6 z power 5. So 6 into e power 5 pi I by 6. Okay, so if you bring it to the numerator, it will become 1 by 6 e power minus 3 pi I by 6 equal to 1 by 6 e power minus pi I by 2, and residue at the point e power 3 pi I by 6. So e power z square means what? 6 pi I by 6 by 6 z power 5. So 6 into e power 15 pi I by 6. So it is 1 by 6 e power minus 3 pi I by 2. Next one, at residue at e power 5 pi I by 6 equal to z square is what? E power 10 pi I by 6 by 6 z power 5 is 6 e power 25 pi I by 6. So it is simply 1 by 6 e power minus 5 pi I by 2. So what's the formula? Integral over c f of z dz is equal to 2 pi I into sum of the residues. So 2 pi I into, so these are the three residues. 1 by 6 is a common factor, take it outside. So e power minus pi I by 2 plus e power minus 3 pi I by 2 plus e power minus 5 pi by 2. Okay, now at all these pi by 2, cos will become 0. Only sine function will come. What is e power I theta? Cos theta plus I sin theta. Okay, cos pi by 2, cos 3 pi by 2, cos 5 by 2 are all zeros. So only I am writing sine value. So minus I sin pi by 2 minus I sin 3 pi by 2 minus I sin 5 pi by 2. Sin pi by 2 is always 1 only, no? But it is whether plus 1 or minus 1 only we have to identify. Pi by 2 is plus 1. So minus I into 1. Here 3 pi by 2 means what? Minus 1. So minus I into minus 1. Here 5 pi by 2 means what? Again the first quadrant. So it will be plus 1 only. So minus I into plus 1. So this I get cancelled. So we get pi I by 3 into minus I. So integral over c f of z dz equal to simply pi by 3. But what's the formula? Integral over c f of z dz equal to integral minus r to r. We can write either f of z or directly we can write f of x dx plus integral over c1 f of z dz. That is integral from minus r to plus r over this line segment and then over this semicircle. Okay, right? Over this semicircle, the value of the integral is 0 by Cauchy's lemma, and as r tends to infinity, this will become minus infinity to f of x dx. This is f of z dz only, but on the real line, z is equal to x. Okay, that is why we can write either f of x or f of z. Both are same only. F of x dx is equal to, the value of the left hand side is pi by 3. So what we get, as r tends to infinity, integral minus infinity to infinity, x square by x power 6 plus 1 dx is equal to pi by 3. But in the question, it is given as 0 to infinity. So 0 to infinity is obtained by dividing the result by 2. Okay, so the final answer is pi by 6. Okay, then next problem, evaluate integral minus infinity to infinity cos x dx by x square plus a square into x square plus b square, where a is greater than b. This is of third model. What the difference between the second and third model is, in the third model you will have either cos or sine function. Okay, but the remaining things are same as type 2 only. Okay, numerator and denominator are polynomial. Degree of the numerator is 2 less than the denominator, and here as extra factor we have cos x. So what is the procedure for this one? Just whatever cos or sine you have, you replace it as e power iz. If you have cos, it has to be taken as real part. The final answer, you have to take only the real part. If it is sine, you take the imaginary part in the final answer. Okay. So since I have cos, I take it as e power iz by, that is replace everything in terms of z. Z square plus a square into z square plus b square. The rest of the procedure are same as type 2 only. Equate the denominator to 0, find out the poles. So z equal to plus or minus a and plus or minus bi. Okay, here they have given a and b both are positive. So that means plus ai and plus bi both are lying in the upper half plane, hence inside, and the remaining minus ai and minus bi are lying in the lower half plane, and hence they are lying outside. Okay, so it's enough to find the residue at the poles which are lying inside C. So residue at z equal to ia equal to limit z tends to ia, z minus ia into e power iz by, you factorize this term. So z minus ia into z plus ia into z square plus b square. So what we get, e power minus a 2 by 2ia into b square minus a square. Similarly for z equal to ib, the residue is minus e power minus b by 2ib into b square minus a square. What is the formula? Integral over c f of z dz equal to 2 pi a into sum of the residues. So 2 pi a into the residues, common factor is 1 by 2i into b square minus a square. So e power minus a by a minus e power minus b by b. Do the simplification. So finally what we get, integral over c f of z dz equal to pi into b e power minus a minus a e power minus b by ab into b square minus a square. What is the formula? Integral over c f of z dz equal to integral minus r to r f of z dz plus integral over c1 f of z dz. By Cauchy's lemma, this value of the integral is 0. And as r tends to infinity, this will become integral minus infinity to infinity f of x dx. The value of the left hand side we found out here. So what we have finally, minus infinity to infinity cos x dx by x square plus a square into x square plus b square is equal to, since there is no imaginary part in the final answer, I write the answer as it is. Okay, then one last final problem. This problem, very simple problem only. This problem I have taken for illustrating you how to proceed when you have a pole on the real axis. When you have a pole on the real axis, there is a slight change in the formula. When you have a pole on the real axis, see, this is a pole on the, see, let me explain with this problem. Evaluate integral 0 to infinity sin x by x. So this problem satisfies all the conditions of type 3. So let me write, since sin x is there, no, I have to take f of z equal to e power I z by z, equate the denominator to 0, the pole is z equal to 0. It is lying on the real axis. When you have poles on the real axis, mark it here and you draw a semicircle over that one and take it as C2. If you have two or more, at all the poles on the real axis, you draw a semicircle around it, okay, right, and find out the residue at the points. So here residue of f of z at 0, that you have to find, and you have to multiply that answer by minus pi I. That is, if you have any poles inside this portion, it is 2 pi I into sum of the residues. But when you have poles on the real axis, the formula is minus pi I into sum of the residues. So integral over C2 f of z dz, that is over the small semicircle, no, equal to minus pi I into sum of the residues on the real axis. So minus pi I into, what is the pole here? 0. So limit z tends to 0, z minus 0 into e power I z by z minus 0. So limit z tends to 0, e power I z, e power 0 is 1. So simply what we get, minus pi I. So we have evaluated what is this C2. Now let me write the usual procedure. Integral over c f of z dz equal to 2 pi I into sum of the residues other than real axis. On the real line, whatever pole you are having, no, omit them. Apart from this, what are the poles? Here, no pole is here for this problem, no. If you have any poles, you calculate the residue and multiply it by 2 pi I. Here for this problem, I don't have any poles here. Okay, so it will simply what? 0. Now, there's a slight change in the formula also. Integral over c f of z dz equal to, usually how will you write? Minus r to r plus c1 only you will be writing, no? That is here. Here you have to write it like, see, that is minus r to this point, then over this semicircle, then this portion. Okay, that is the real line is here partition into 3 parts. One is this line segment, another one is this curve, another one is this line segment, and then over this c1. So integral over c1, that is always 0, that we know, and then here simply you can write minus r to r. No need to split it like that here. You can simply write minus r to r f of z dz plus extra one factor. What do you have here? Integral over c2 f of z dz. Okay, this value is 0 by Cauchy's lemma. This value I found out to be minus pi I here. So substitute minus pi I, and this value as r tends to infinity, it will become minus infinity to infinity f of x dx, and the value of integral over c f of z dz is 0 because there is no other pole here. If you have any other pole here, you will get some value. Here, as there is no pole, it's 0. Okay, so integral minus infinity to infinity f of x dx is equal to simply what? Pi I. Okay, right. Pi I by 2 is the answer. But what is the actual problem? Sin x by x, no. Sin x means what? Imaginary part of the answer only you have to take. So what is the imaginary part here? Only pi by 2. So pi by 2. Okay, right. That's all. Thank you.